That was the title or some variation of it. So the first speaker today is Philip Phillips, and he's going to tell us about Wigner crystallization in twisted bilayer graphene and TMD systems.
Thank you very much. And I would like to thank the organizers. I know this is old hat to say, but I really do appreciate this rather very short notice. And this is an incredibly timely topic and one that is very dear to my heart. So I'm very glad to be involved. So my collaborators are a student of mine, Bikash Padi, an ex-postdoc, Shandon Sethi, and a colleague of Attach's actually in Switzerland, so who became involved in the Fukuyama-Lee type analysis of the pinning potentials for Wigner crystals. So the problem is, what is the nature of the insulating states? And I would just like to show the evolution in terms of what people have advertised as what the insulating states are. In 2018, it was viewed as MOT, and 2019, 11 months later, these were called correlated insulators. And it's this evolution, it's in this evolutionary period that we were started to work on this problem. And we have always said that these, in fact, are Wigner crystals. All that view was not necessarily popular. But the field began to receive much more interest, or this view rather, with the TMD materials, and in the sense that this state was called a Mott insulator when you had an integer number of electrons in each of these cells, but the fractionally occupied states could not be called Mott insulators since they break symmetries. And it's because of considerations of this point that we were led to this view that perhaps all of these insulating states are Wigner crystals. And one can appeal to any number of, multi-orbital types of Mott effects. None of that will give rise to an evolution involving new spatially resolved structures. Okay, so the question I want to ask is there a single mechanism for the insulating states in all of these materials? And I'm going to argue that in fact there is, and that the Wigner platform offers a comprehensive scenario for that. Okay, so just to review briefly Wigner crystallization. There's no underlying lattice. You break, of course, the continuous translational symmetry. In 2 dimensions, we note that the underlying structure is a triangular lattice. RS has to exceed 37. The problem with Moiré systems is that it's a Wigner crystal in a periodic potential. And that's what we generally mean by a generalized Wigner crystal. The Mott scenario requires an underlying lattice, the symmetry is intact, and one can work out what the Mott criterion is simply by looking at a hydrogenic type of system where the separation between the atoms is the key player in driving the dynamical metal insulator transition. And this criterion is roughly this. And what I want to show is that this criterion for the insulator metal transition is nowhere near is not satisfied in any of these systems, and hence this is a non-starter. Okay, so the general problem for Mottness in TBLG is that since all of these fillings are less than the band filling, one would expect to see an insulating state for all values of nu less than 4. And this is what initially piqued our interest. If you look at Pablo's data, there is no insulating state at nu equals 1. And this trend continued. Look at Yazdani's data. This is now the conductance. Very nice insulating behavior here. Here's the dip. At nu equals 1, there is no insulating state. There's some feature. And if you look at Efetov's data later on, you find, yeah, there is some peak here. And you see a much more defined peak at nu equals 2 and nu equals 3. But nu equals 1 seems rather weak. And the question we asked is why? And this is the data rather from Corey Dean's group. And also at nu equals 1, there is nothing. Nu equals 2 and 3, yes, there is a peak that you could associate with some sort of underlying insulating behavior. They did, of course, see an insulating state at nu equals 1 when you applied pressure. And I think this is the only observation of this kind. But this is also something that one has to keep in mind. Why is it that you need pressure to make this state, which was not at all insulating? If you look at this featureless conductance, why is it that the pressure induces an insulating behavior? But still note, this is much weaker than this or this.
Philip?
Yes.
Can I say something? Actually, the resistive peak at nu equals 1 has metallic temperature dependence. It's not insulating. There is a resistance peak, but it's metallic in, as far as I know, all the data, including ours.
This is what I'm showing right here.
Oh, okay.
Okay. So you have to be careful just looking at peaks, as Pablo has pointed out. Only in when you apply pressure is in fact this behavior is the slope of dg dt consistent with insulating behavior. In the absence of that, it's metallic. Okay, so this adds to further intrigue as to why, if this is a Mott scenario, why is nu equals 1 different from all of the others?
No, Philip, that's nu equals 2. That's not nu equals 1. That's nu equals 2. You can see.
This is nu equals 2. I asked them about nu equals 1, and they said it's the same behavior. Okay, so they never published that data, but they said it's the same behavior. Okay, now, one of the questions that arises in this field is, what is the nature of, what exactly is the potential? Does the long range part of it, is that relevant at all? People want to say Mott will just focus on a very short range potential. So experiments were done to see what happens as you change the distance this gate is from where the electrons are. And so you are screening the potential. And as you increase this screening, what happens is this feature here at the insulating states go away. And as you can see, they come back when the gate is sufficiently far away. There's a distinct peak at nu equals 2 and 3, but there's a very small feature at nu equals 1. Okay, and this was, so yes, this is important. And this is Andre Young's data. You also see a reemergence of the peaks at nu equals 2 and 3, but in fact, there is nothing going on at nu equals 1. And consistent with their earlier data, when the gate is sufficiently far away, so it's unscreened, so even when it's, right, so this is not there, and even when you introduce this gate that is much closer, of course, there's nothing going on here. But the state here at nu equals 1, which should be there, doesn't seem to be there. Okay, so what we have then is the following puzzle. We have a hierarchy of insulators. Nu equals 2 seems to be the most prominent, then nu equals 3, and then nu equals 1. What exactly nu equals 1 is anyone's guess, but it seems to have a different character. Okay, so trying to explain this all under one rubric is the general problem. Now, the problem one faces if one wants to attribute all of this physics to Mottness is that you have to arrange n charges per unit cell without breaking the underlying triangular symmetry. And this is impossible if n is bigger than 1. You have to put the charges somewhere. And it's certainly not possible if you have fractional occupancy. Okay, so it's because of this that we were led to just take a step back and consider this problem to be one of just a dilute electron gas in a periodic potential. So we concluded that, in fact, one should think about just putting electrons into the system. There's a periodic potential which might provide some pinning. So one should think about these as just Wigner crystals. And the type of Wigner crystal that is the most prevalent in 2D is just this triangular lattice where you have one electron per cell. And this forms for RS bigger than 37. Now, trying to come up with the other ones for nu equals 2 and 3 required some thought, but with the help of David separately, we were able to conclude that these are most likely this honeycomb lattice and this kagome lattice. And these are all deformations of the triangular lattice by just changing the unit cell edge length. And this will manifest itself in a change in the critical strength of RS. Here, this requires an RS of 21 and this 18.5. So each of these has a diminished value for the critical RS, nu equals 1 having the largest value for the critical, for its formation. Okay, so what we want to do is look at a realistic model for twisted bilayer graphene and estimate what RS is. Now, if you have a Dirac spectrum, you know it's a non-starter already. RS is a constant. But that's not what's going on here. If you look at a relatively accurate low energy theory, you find, in fact, that the band dispersion has quadratic, cubic, and quartic terms. There's a flat band condition, and what you are attempting to do now is use this sort of dispersion that comes from this Hamiltonian to deduce what RS is. This can be done. RS will contain a factor which depends on the angle, on the twist angle, and it will also depend on a factor which now depends on the filling or the density. And because these bands are chiral, in fact, this will be non-monotonic. Okay, so filling dependence will be there. And that's demonstrated right here. So RS will depend, in fact, on the density, but it will also be determined by the twist angle. And here we have the thresholds for nu equals 3 and nu equals 2. The key point is that the experiments in terms of twist angle are right around here. So as you see, the experiments cross this curve here, but they don't cross this one. And note, this has a very narrow window in terms of magic angle homogeneity that is required. Here it's much broader. So an explanation then of why nu equals 1 might be special is that you don't cross this threshold. Now, another feature is here, and this is the Mott criterion. Okay, the Mott criterion, there's a break right here, occurs at when this twist angle is 0.7. And we can understand that the following way. The Mott criterion, in other words, where's the metal insulator transition, is roughly this quantity right here. And since this has the effective mass in it, this is a dynamical criterion. So one can just use this funky dispersion that one obtains from this low energy Hamiltonian, take the derivative, get the effective mass, and what you find is it looks like this. And then the Mott criterion is that this whole quantity must be less than the dielectric constant. Well, this is roughly a constant. Lambda s is the Moiré edge length. That's much bigger than A0. So it's impossible for this quantity, when this thing is roughly 150 to 200, to be less than epsilon. So that's why we said very clearly that, in fact, the Mott criterion is not satisfied in these systems, and hence you should not think about this in terms of Mott physics, because this is never satisfied. Okay, now what about hydrostatic pressure? The band structure was done by Efthymios Kaxiris. Let's just look at the two lowest line bands. And as you increase the pressure, of course, the bands compress. And this is not monotonic, however. As you increase the pressure even further, the band dispersions begin to broaden. and hence one should expect to see that RS is increasing and then it's decreasing. Okay, and that's exactly what you find. So as you increase the pressure, there is a window over which you cross the threshold for 37, and that's between here and here, and then it goes back down again. So with this, we were able to explain why it is that nu equals 1 seems to come out as an insulating state only in the presence of pressure. Okay, now one can estimate what the rough Coulomb repulsion is. It's around 30 MeV. And if this is a Wigner crystal, one expects the Lindemann criterion to give you melting when you have basically 1/100th of this value, and that's roughly 4 Kelvin. So the order of magnitude of the numerics seems to all work out. Okay, now I'd like to come to this issue of the negative compressibility that I raised yesterday. A Wigner crystal is a state which comes about because the uniform density state is not stable. That can manifest itself in any number of ways. One way it can manifest itself is that there's a negative compressibility. That's simply telling you that the uniform state is not the ground state. Now, I asked Pablo about this a long time ago. We had a correspondence, and he wrote this very nice paper in which it was stated very clearly that the negative compressibility, which we'd expect for an ideal Wigner crystal, is not seen. So that was PRL 2018-19 rather. But of course, you know, there's this data out there in which you see these periodic negative dips to the compressibility as a function of filling. Now this was talked about yesterday in the context of Hartree-Fock. I tried fitting this yesterday to this 1 over square root of n that you get from Hartree-Fock. That doesn't quite work. So I don't understand this data in this general, in the broader context of what it's actually saying in terms of Wigner crystal formation. And that's one of the questions I would certainly like answered in this conference. Okay, so this is all I want to say about twisted.
One comment is that negative compressibility is very asymmetric. You see it on one side of the transition.
Yes, that's right.
Nu smaller than 1 or nu smaller than 2, but completely not on the other side. So I don't know how a model of a crystal would account for that. Okay,
so they have different masses. So and this will become clear when I talk about the dichalcongenide materials. The Wigner crystallization is not symmetric with spectrum electrons and holes. Okay, but this right here.
Can I ask one quick question, which is at nu equal 1, where you say it's a Wigner crystal, you basically have 1 electron per unit side. Mm-hmm. So in a sense, you are not breaking any symmetry. It's exactly the symmetry of the original Hamiltonian. So in that sense, is it a Wigner crystal, right?
It's a Wigner crystal in the sense that RS has exceeded the value that you are asking a question about the kinetics of the system.
Okay, but in terms of counting, I get 1 electron per site. I don't get any breaking of symmetry.
No, there is what. As I said, Mike, since we know that we can change the filling and we see this hierarchy of insulating states, the question is, do we make a distinction between what's going on at nu equals 1 and all of the others, which in fact do require some sort of symmetry breaking? Can all of them be understood within one rubric? That's the question I ask. Okay, and as far as I can see, there's no reason to assume that nu equals 1 is special.
I mean, you said that it's special correctly, that it doesn't show the gap.
That you need to go and invoke Mott physics to explain what's going on at nu equals 1. Okay.
Okay. I'm just trying to understand whether you should call it a Wigner crystal at nu equal 1. At nu equal 2, 3, maybe, but at nu equal 1, is it? Can it be that you have not one electron per site, or maybe it's more dilute or something like this, then you break a symmetry? Or you really think about a state where it looks like MOT, it just with a large R sub S?
Okay, so as I said, if you go and evaluate the Mott criterion, N sub E A0 star approximately 1, you find that this is not satisfied in these materials until you're at a density at least 3 orders of magnitude larger. So I think Mott is a non-starter from the get-go. And the reason why nu equals 1 is hard is that that's the one that requires the largest value of R sub S. Okay. Now, the TMD materials. These are on some level less controversial. The only distinction is whether you have the same chalcogen in both of the layers. People have done calculations to see if they satisfy the Wigner criterion. There's this paper in 2017, and even if you have a valley degeneracy, you can still get the signatures of Wigner formation. And this paper has worked out that in fact it's around 29.5, so it's less than 37. And this is now the periodicity of the Wigner lattice. And so all of this can be worked out. And you'll see that there's a big distinction between whether or not you have electrons or holes being the carriers in these systems in terms of whether or not you satisfy the Wigner criterion. Okay, so we just created a table and we culled this from all of the available literature. And for the homo bilayer materials, the crucial thing is right here. And you see in these molybdenum disulfur or diselenide, these are ideal materials for forming Wigner crystals, as you've seen in the experiments with Professor Park and his collaborators. Once again, we can also evaluate the Mott criterion, N sub E to the 1/2 A0 star for these systems, and you're 3 orders of magnitude away from what you would need to really talk about Mott physics. So this is a consistent theme in all of these Moiré systems, and hence I don't see how one can continue to talk about these insulating states as having anything to do with Mott physics. Okay, so these are the hetero bilayer materials. Sorry, these are the homo bilayer materials. Now we go to the hetero bilayer materials, these mixed materials here. And the chalcogen is of course different. And here you see the asymmetry between electrons and holes. The holes work out much better than the electrons because of the difference in their effective mass. And there's a maximum nu that you can have in these systems, and the melting temperatures are roughly around this order. So it's not so different from what's going on in the previous systems that I mentioned, the TBLG. Okay, now a system which has been getting a lot of attention is the ones formed out of molybdenum. And as you can see, they have the holes once again work best. In some of these, you can get the electrons to crystallize, but definitely if you're working on these systems, the holes are definitely the way to go. And at these densities, this is the value of R sub S. Okay, so these I would say are much less controversial. Others, in addition to us, have reached the conclusion that they seem to be the ideal platform for Wigner crystal formation. Okay, and in fact, if you look at the most recent data from Ji Shen, she in fact has tabulated a series of fractional insulators, some of which she ascribed to the underlying cause of being a Wigner crystal formation. Okay, so I think this platform should be explored much more vigorously to see if it, in fact, all of the collective excitation types of physics that you expect for a Wigner system is in fact there. Okay, now, Wigner formation in the presence of a Moiré potential is a very different problem, different sort of platform than the original reason why Wigner lattice formation was introduced in the first place, because there's an underlying potential. That doesn't mean you can't talk about Wigner formation or that you need to talk about Mott physics. That is not correct. You're talking about a system which has a well-defined Brillouin zone, and the underlying potential is created by something which also has its own Brillouin zone. And here are the relevant length scales here. So the actual spread of the wave function is much smaller than either this length scale or the Wigner length scale. So what one would have to do to answer the question about the dynamics of a Wigner crystal is just go and work out what is the pinning that comes about from the underlying Moiré potential. So
Philip, you have 5 minutes.
That's perfect. I think I should be done in 5 minutes. One has to go and work out what are the excitations of these systems. So the charge density, you just expand it around the home position, and you want an elastic theory in terms of these deviations. And so you expand this in terms of gradients. You can represent everything in that way, the electron-electron interaction, and then also the interaction between the electron and the lattice degrees of freedom. As I said, this is identical to the problem that Fukuyama and Lee worked out, except it's not disorder that's providing the pinning. It is the underlying Moiré lattice. So all of the details of this can be worked out. We did this in collaboration with Chitra and my students and postdocs. And so you bring this into quadratic form. There's a dispersion which looks like this. We work with a generalized Coulomb interaction, which goes as Q to the minus gamma. So I can change the range of the interaction. And as you see, one can have a completely gapped spectrum or one that vanishes here, depending on the range of the interaction. Okay, now the spectrum, the one that's most relevant for D equals 2 is, of course, gamma equals 1. And the spectrum will, of course, acquire a gap. And there's no simplification of this expression. This just means A is just indexing perpendicular or parallel components. This vanishes when this is this. Hence, the melting temperature depends on the twist angle. And if we use the insight from the Fukuyama-Lee paper, the pinning potential roughly scales as this quantity divided by rho 0. And hence, it's directly related to the wave vector for the underlying Moiré lattice. And hence, it's inversely proportional to the size of the Brillouin zone. Okay, now, I know I've shown data which says that, in fact, the insulating behavior seems to be divorced from superconductivity. I don't exactly know what to make of that, but I just want to remind you of something that we said a very long time ago when I was working on a slightly different problem, but once again, I attributed that physics to Wigner behavior. And one can argue that Wigner crystals are close to a superconducting instability. If you remove electrons from them, there's a retardation effect, which collectively leads to an attraction between the electrons. And it's good that this is retarded, and it could, in fact, mediate some kind of superconducting instability. And that was the whole point of this paper 22 years ago. Whether or not this is relevant to what is going on, I do not know, but I would say that Moiré is certainly different in that I think it is bringing up this problem, which doesn't seem to be going away, of what relevant states are in the vicinity of melting a Wigner crystal or deforming a Wigner crystal, the relevant excitations. And this was an unsolved problem a long time ago, and it's still an unsolved problem now. And I think these TMD materials, and also twisted bilayer graphene, might be an ideal platform for exploring some of these questions. So that's what I wanted to say.
Okay, thank you very much. So now we have time for questions. So Philip.
Oh yeah, it was kind of great talk. I have one question regarding the Chern numbers, potential Chern number appearance onto the band right after this gap opening. Anything that we can learn about this Chern numbers, potential Chern numbers out of this type of the Moiré insulator?
The fact that I haven't mentioned that sort of shows my bias. And so I don't want to say anything to incriminate myself, okay? Let's just keep it all positive. That's all, yeah. I have nothing to say about that, okay?
Eugene?
So, very interesting talk. So I have a question again, just to make sure I understand your argument for why we should. It's like talking about like this Moiré states as Wigner crystals is better. So can I formulate it like this? If I look at Coulomb energy scales like characteristic of kinetic energy, they are higher than the super-lattice potential, and that's why you are saying, oh, I would rather think about it as intrinsically Wigner crystal, and then just added like a bit of super-lattice to convert it into this Fukuyama-Lee problem. So it's all about energy scales. So you're saying that the super-lattice is just small energy scale.
Yes.
So roughly, and is this number like 10 to minus 3? Are you saying that the super-lattice potential is 10 to minus 3 of the characteristic kinetic energy?
Okay, I don't remember the exact number. That's roughly, I would say, yes.
Okay, I understand now. Mm-hmm.
I'm a bit surprised about that. So I think the reports, maybe Kin-Fai can say more about it, but I thought that the Moiré potential is comparable to the off-site and the on-site interaction. But maybe Kin-Fai, would you like to say?
Well, we didn't find that. So if you just look at, sorry, that's a no. So in other words, you would be asking. Yeah, that's a number that's scaling like, 1 over the size of the Brillouin zone. So I don't see how that number is.
If you're talking about maximum to minimum, the Moiré potential, I think that's actually comparable or slightly bigger compared to the on-site potential. Or maybe Feng can comment on that. As far as I know, they are sort of comparable or even slightly bigger than the on-site.
Yeah, I think the potential maximum to minimum is at 100 millieV or larger. So
it's probably comparable to the U.
Yeah, it's comparable to the on-site Coulomb potential, much larger than the nearest neighbor.
Yeah.
Right.
I see, but then somehow like it feels like it's more like in between Wigner and Mott. I mean, it's sort of.
Yeah, that's why we never call it the real Wigner. It's called the extended Wigner crystal. It's like a Wigner crystal, but they really get pinned by the lattice. So the long range,
that's been my point, which is why we went and did this Fukuyama-Lee analysis. But it's the potential that's causing the pinning.
So, Yong-Yon, you have a question?
Hi, yeah, thanks for the nice talk. I was wondering about the, yeah, I think probably this is along the line of question by Philip, but it's realized that the TBG flatband has some topological obstructions and also trend numbers has been observed. So I was wondering whether this Wigner crystal formulation to approach this problem is okay, even when localized binary orbital description doesn't seem to exist.
Right. So that's one of the reasons why we stayed away from the Hubbard types of descriptions, which would require a really localized description. When you go and calculate RS, you don't need to, I mean, you don't need that. You're simply asking the question, what are the kinetics of the system? You don't require a tight binding description.
So actually, only selected homo twisted bilayer people say they are topological, but like for the hetero TMD bilayers, they are not topological at all. It's just very simple flat band.
Yes, that's right. That's right. That's right. So I have a question for Pablo. What do you make of your data?
What data do you mean? I mean, you mentioned it is true that
so in 2019, no negative compressibility. 2020, there seems to be something going on.
So first, let's discuss first some logic sentences. Wigner crystal implies negative compressibility. Mathematically, non-negative compressibility means not Wigner crystal. It doesn't mean negative compressibility implies Wigner crystal, right? We agree on that, right? So A imply B means not B implies not A, but it doesn't imply B implies A. So that's something, it is true, in those early data, we didn't see negative compressibility. Now, with better samples, we do see negative compressibility. I completely agree in the paper, first with our paper with Shahal, and then we did it in our independent measurements of chemical potential. I'll mention that in my talk later today. So now, there are many reasons why one can have negative compressibility. If the only reason in the universe that one could have negative compressibility was Wigner crystal, I would agree that implies Wigner crystal. Now, there are many circumstances under which you can have negative compressibility. In fact, we have a simple model, admittedly very simple, but again, it's an experimental paper, so please forgive us, a very simple model in our paper, which does produce negative compressibility. Now, having said that, I'm of course, I'm experimentalist and I present data. I let much smarter people like you to figure out what it means and how to make a model that explains it, okay? I'm not opposed at all to considering Wigner crystal. I think that one thing that, as Shahal was asking, one has to look at the details. For example, the negative compressibility appears in a substantial doping range before nu equals 1, also before nu equals 2.
Right. It's a periodic
function. But right after nu equals 1, right after nu equals 2, it goes to very positive. Right. If this was a Wigner crystal as a function of doping, I would expect it to exhibit negative compressibility also at 1 plus epsilon, not just at 1 minus epsilon. But maybe I'm missing something there. So it is, I think it certainly deserves careful consideration.
Certainly, if you have a Wigner crystal with a pinning potential, you would not have a negative compressibility.
But at why? I mean, what changes in your picture of a Wigner crystal between 1 plus epsilon and 1 minus epsilon?
Okay, I'm not saying I have an explanation for that. I'm just saying that one thing you should think about is if you did have a pinning potential, you wouldn't get a negative compressibility. Okay? So
but we do have a pinning potential. We have the Moiré potential, right?
Yeah, I know. So Your original statement is that if you had a Wigner crystal, you would have a negative, that you're saying Wigner crystals have a negative compressibility. A way around that is if it were pinned, in which case it would not be that way. Even if it's still a Wigner crystal.
It turns out we do have negative compressibility.
Yeah, so now you have negative compressibility, okay?
But that's perfectly, I mean, that's interesting. It doesn't, what I'm saying is it does not necessarily imply Wigner crystal without pinning.
Look,
or with pinning. It doesn't imply because there are other models that give you negative compressibility too.
Negative compressibility, like 2.2. If you look at, you know, David Sepperly's simulations, 2.02, you have a negative compressibility. He has a Wigner transition at 37. So this negative compressibility is not associated necessarily with that. Okay? So, but the thing of it is, yours is a periodic function of nu. So that's a further fact that we have to explain. And I don't know of anyone who can explain that.
No, I mean, as I said, the simple model that we have in our
but that's a mean field model that you wrote down, which is not valid for the strong interactions that you have.
So, well, as I said, if you can try something with a simple model first, you try something with a simple model first.
Yeah, but don't
if it captures some of the physics.
Look, if the system's strongly correlated, I can write down something that's not valid and explain something. That's not smart.
Okay, I'll quote Sankar, who said yesterday that, you know, Hartree-Fock makes a good job with compressibility, even in the strongly interacting case.
No one is
doubting I'll let Sankar defend his statement.
No one is doubting.
So guys, I think that maybe we should leave this to the discussion session later this evening. So Shahal has a question, and maybe then afterwards we move on.
So maybe I won't ask my question, but I do want to add one more piece of interesting physics. So Pablo and us have a recent experiment that shows that near nu=1, there is a Pomeranchuk effect. Now, we heard yesterday that Pomeranchuk effect is exactly what you would expect when you go from a Fermi liquid to a Wigner crystal. The only problem is that we see the solid kind of behavior on above nu=1. Okay, we see that the spins are free there, but there we see positive compressibility, metallic behavior, and no signs of any thermodynamic gap. So it has a smell, let's say, of a Wigner crystal in this sense, in this Pomeranchuk sense.